Hello, this is Miguel Cabrera from the Scopus Institute of Science and Technology, Scoltech. I am glad to present our work, LinkGlide-S, a wearable multi-contact tactile display aimed at rendering object softness at the palm with impedance control in VR and telemanipulation. Nowadays, teleoperation and telepresence represents one of the most natural applications of haptics, while the most effective combination of various haptic feedbacks remains to be subject of active research. Many virtual reality applications have been introduced, such as simulators and games, and are becoming part of our daily life. In the last years, remote telemanipulation has shown significant improvements and many applications in different areas, such as aggregation of nuclear waste, telemaintenance, and micromanipulation. The implementation of haptic feedback to the users during telemanipulation provides many advantages, such as increasing the spatiotemporal coordination in collaborative environments, etc. Here we can observe the robotic system Da Vinci, which is used in medical applications to make surgeries less invasive for the patients. The surgeries are done by doctors with some kind of joysticks, which allows them to manipulate inside of the human body. In the left you can see a robotic system that are located in the International Space Station, which can be teleoperated even from the Earth. For these applications, it's very important to implement haptic feedback to improve the skills of the operators while performing these very precise tasks. The palm of the users plays an important role in manipulation and detection of objects. The interaction force between the object and the palm determines the perception of contact, weight, shape, and orientation. The density of the receptors located on the fingers is 5 times bigger than the density of the palm. However, the overall receptors numbers on the palm is compensated by the largest area, having 30% of all the receptors located in the hand, glabrous skin. For this reason, it's important to take advantage of the palm and develop devices that stimulate the most significant area by multi-contact points. As we can see at the top left, Choi et al. Introduced wearable devices that deliver the sensation of weight and grasping of objects in virtual reality. These devices are located on the fingers, where unidirectional brakes create rigid grasping kinesthetic feedback. At the top right, Tirado et al. Presented a device that delivers softness, hardness, and stiffness feedback using electrical stimulation. The third work presented a device which was calibrated by the BioTAC. This calibration was done to render the right stimuli on the fingertips. This device was implemented while teleoperating a robotic system. The last work presents a haptic interface to represent the stimuli on the fingers and the palm. At the fingers, kinesthetic feedback is provided. However, the stimuli on the palm are just static contact points. In the present work, we are introducing a novel wearable haptic interface, LinkGlide-S, and an extended perception study of the multi-contact stimuli on the user palm. The wearable tactile display LinkGlide-S is designed to provide multi-contact stimuli on the user palm. This with the goal to achieve realistic rendering of object perception during the detection and manipulation in virtual reality environments and to transfer the information during telemanipulation. The first part of the work presents the LinkGlide-S configuration. The second part illustrates the impedance control used to deliver the stiffness stimuli. And in the last part, 3 experiments are carried out to evaluate the user's perception. LinkGlide-S provides the sense of touch at 3 different points on the palm of the user, where multimodal stimuli can potentially be delivered. The proposed device is based on the inverted fiber linkage mechanism. The LinkGlide device was designed to adapt to the user's hand ergonomically, improving the operability of the fingers in comparison with the previous version. It has a total weight of 270 grams. 3 to 2 degrees of freedom inverted fiber mechanism distributed in parallel planes produce a sliding force and multi-contact state at the palm by 3 contact points. Each of these systems has 2 servo motors. Their angles of rotation are controlled to locate the single end effector on the 2D coordinate systems as shown in the figure. The base of the device consists on 3 modules connected by metal pins, which allows the rotation of 15 degrees in both directions to adapt to the position of the user's hands while opening and closing. In each of the 3 contact points, one force-sensitive resistor, one force sensor, was installed, as shown in the figure. The principal goal of the force sensors is to measure the normal force generated in each contact point. The sensed force is an input for the impedance control, which is proposed to provide the sensation of the object's stiffness. We propose an impedance control to implement rendering of softness by the LinkGlide-S device between the virtual object and the hand. The stiffness of the contact point depends on the force delivered to the palm. The force delivered to the palm from the haptic device is generated in the virtual environment and represents the force with which the virtual object touches the virtual hand. When the virtual user approaches a virtual object, the impedance model is used to control the force to be delivered to the palm. The impedance control generates the end effector trajectory that goes through the hand. Therefore, the device could be in the same contact point but delivers more force or less force according to the hand's position. The factors for the mass spring damping link can be modified to provide different stimuli. In the figure, the contact point expected position, the real position, and the hand position are rendered while the impedance control is activated using an undamped response. 3 different experiments were carried out. The first one to evaluate the user perception of the patterns delivered at the human palm. The second, to assess how the device helps to improve the user's experience in a virtual reality environment. And the third, to study the user perception of stiffness patterns using the impedance control. The first experiment focuses on the perception of the patterns on the palm using LinkGlide-S. In this experiment, 11 tactile patterns have been designed, as shown in the figure, where the red circles represent the contact points on the palm. Each pattern was delivered for 2 seconds on the user's palm, and after each of these patterns was displayed 5 times in random order. 16 volunteers participated and completed the test. The experimental results are summarized in the confusion matrix. The average recognition rate is 78.1%. Pattern 2 and Pattern 9 had the lower recognition rates, or 62.5% and 65%. To determine the statistical difference in pattern recognition, we conducted an one-factor ANOVA without replication with a chosen significance level of 0.05. According to the ANOVA results, there is a statistical significance difference in the pattern recognition of the users. These results suggest a large effect on the recognition due to the different patterns rendered. The parity test with one step of error correction showed the statistical significance difference between the recognition of the pattern 4 and pattern 11, and between the pattern 6 and pattern 11. The second experiment aims to investigate the realistic perception of objects interaction using the proposed device in virtual reality. 3 patterns from the experiment 1 were selected and used to render the spherical object's surface. The results will help to develop the best strategy to create tactile sensations with available 3 contact points. The users were asked to wear the device on the palm and a head-mounted display HTC Vive Pro. A virtual reality environment was designed in the game engine Unity 3D. The 3D environment consists in 3 spheres of 25 centimeters in diameter, located at 1.2 meters, floating over the virtual floor, as shown in the figure. The users were asked to rate the similarity of the haptic sensations rendered by the device patterns to the real interaction with the object, from 1, the lowest, to 5, the highest. In the virtual 3D environment, the user was asked to interact for 1 minute with each of the 3 spherical objects. When the user's virtual hand contacts the surface of the spherical object, the specific tactile pattern is activated by the haptic display. Pattern 1, 2, and 3 from the experiment 1 were selected. 7 participants completed the experiment. The similarity perception rates during the interaction with the spherical object surfaces are presented in the figure. To determine the statistical significance between the user's grades, Friedman test with a chosen significance level of 0.05 was performed. A statistically significant difference was found between the similarity patterns rates. Wilcoxon tests were done for pairwise comparison for the 3 pattern similarity perception rates. According to the statistical significance difference, it was found that the interaction with a 3D sphere with patterns 2 is more realistic comparing with the pattern 3 and pattern 1. Based on this evidence, the pattern with the lowest recognition rate in the first experiment obtained the highest similarity perception during the interaction with the spherical object surface in the virtual reality environment. The last evaluation was performed to analyze the human perception of the different stiffness of objects delivered on the palm by the haptic interface. The information from the force sensor and the contact points was used to deploy the control techniques. We proposed two control approaches for the tactile interactions. The first one is the force control. The device and effectors move to the palm until it measures the limit force. Then the device returns to a not contact position. And the second is impedance control. The device interaction with the user's palm uses the impedance control equations described before. For both cases, the three contact points are located using the pattern 2 of the previous experiments. We tested three different stiffness values in the experiment, strong, medium, and low for each control technique. The parameters for the tactile patterns are shown in the table. Each pattern was delivered on the palm 5 times in random order. 6 participants completed the experiment. This study was divided into 2 parts. During the first part, the experimental procedure was implemented for the tactile patterns using the impedance control. In the second part, the experiment procedure was implemented for the tactile patterns using the force control. The experimental results are summarized in 2 confusion matrices for actual and perceived patterns across all the subjects. The first table contains the data for the impedance control patterns, and the second table shows the data for the force control patterns. The pattern perception was analyzed using a Friedman test with a chosen significance level of 0.05. A statistically significant difference was found between the patterns delivered by the impedance control. No statistical significance difference was found between the patterns delivered by the force control. Wilcoxon tests were performed for pairwise comparison for the 3 patterns that implemented the impedance control. According to the statistical significance difference, pattern 3 is more recognizable than pattern 2. We can conclude that impedance control effectively presents the stiffness of the objects to the user's palm. In this work, a novel wearable multi-contact tactile display was presented. An extended perception study of the multi-contact stimuli was performed, and the implementation of the impedance control for object stiffness rendering was introduced and analyzed. 3 different experiments were carried out. The first experiment evaluated the user perception of the tactile patterns at the user's palms. The second study analyzed the user's sensations while interacting with the spherical object surfaces in virtual environment. And the last experiment studied the user perception of the stiffness patterns using impedance control. In future work, different impedance parameters and tactile patterns will be explored in virtual reality applications to verify the perception of different shapes. The collaborative robot's teleoperation will be implemented, and the user's perception will be explored, such as the force perception by a remote robotic gripper during the grasping of deformable objects. LinkGlide-S can be used to represent the sensation of virtual objects on the palm and potentially in other places of the body. The proposed display can be used in many applications, such as in effective haptics, in robot bilateral teleoperation, and teaching robotic systems using the human skills. Thank you very much for your attention, and for further information, here you can find my contact.